Hi everyone, welcome to this video, and today we'll be talking about system responses in time domain. However, we will find them first using the Fourier transform in frequency domain. So let's dive into the first question with just showing the steps how to find the step response of the following transfer functions. We'll be going over 3 examples in this tutorial, and we'll show you how in the different configurations that we can find out the step response of this transfer function. So you would imagine that the total transfer function of a system with or without any feedback is going to be given to us as follows, which is GS. It's in frequency domain, S domain. However, we need to find the step response of that, which means that essentially if we are given step as the input of the system. So I would write Rs equals 1 over S as the input, because the input of a step in frequency domain is represented with 1 over S. And that is going to be applied to a system with a transfer function of GS. The output CS is what we are after. In the CS and frequency domain is simply Rs times GS. We just need to convert CS back into time in order to find the behavior in time for this function. The way that we approach this question in general is to solve everything in frequency domain using Fourier transform, since everything is going to be algebraic and easy in terms of calculations, which would be only multiplications or divisions. Then at the very end, we'll convert back whatever that we get in the frequency domain as the output of the system back into the time domain using the uh, inverse Fourier transform. So that will be our main approach here. So in this case, let's start with this question A. So the GS is given as follows. So CS essentially is going to be 1 over S times 400 divided by S squared plus 12S plus 400. In this example, we're dealing with a second order system essentially, that the roots are not readily available for us and the numbers are not very easy to calculate the roots. We just need to break it down into simpler pieces in terms of the first or second order roots for CS though. So we need to convert the result of this multiplication into summation or subtraction of simpler pieces. And in order to do that, we would assume that one of the roots, which is 1 over S, or the root, one of the poles that is at origin, is going to represent itself at the final result again. So we would consider that at the very end as well. But we don't know what coefficient it might appear with, so we would call this generally with a coefficient of A. And also, we know that this second order system, the roots of that, which cannot be simplified much easily, is going to appear as part of our result at the end. However, since this is second order, the numerator would now should be first order. So I would call it BS plus C in the most generic form. And we are trying to find what are A, B, and C. Because in doing so, we can then convert A over S back into time, and also this fraction back into time using the table of inverse Laplace transform much easily. So in order to find A, an easy approach for us is to think about it, that this this equation holds true for almost all values of S, as long as the denominators are not going to be 0. So if you want to make sure that A is going to be calculated easily, we can replace S with a known value and then evaluate both sides with respect to that value. So in this case, I can multiply both sides of this equation by the denominator of A, which in this case is going to be S. And if I do so, this second equation is going to be multiplied by S as well. Similarly, the first part is going to be multiplied by S, and this guy is going to be multiplied by S. At the very end, if I replace S to be 0 in the second stage, where I don't have any S in the denominator, I can easily get rid of this secondary term because that's going to be multiplied by s, which is 0. And the first term is going to be calculated only for this part at s equals 0. So that would lead me to find a much easily. So let's do that really quick. If you multiply both sides by s, what I would get, first part of the equation is going to be 400 divided by s squared plus 12s plus 400. And the second part is going to be a plus s times bs plus c divided by s squared plus 12s plus 400. Now, I know that this equation holds true for all values of s, as long as denominators are not going to be 0. An easy value for s for me to find a is something that I could get rid of the second term. And that is nothing but 0, because at s equals 0, this multiplication is going to vanish. So if I calculate both sides at s equals 0, the first part is going to be 400 divided by 0 plus 0 plus 400, which is equal to 1. And the right side it would be a plus 0, which is equal to a. And in this case, I can easily find out a, which equals to 1. So far, I could find a to be the value of 1. Now, we can move forward and try to find what are the other coefficients of b and c. So if you want to think about the same strategy and try to multiply both sides of the original equation by the denominator here, we don't have explicit roots for this equation, and that would be quite difficult for us to find the roots and evaluate the roots on either side of the equation. So a better approach in this case is not going to multiply the denominator at both sides by second order equation. However, since we know that this equation holds true all the time, we can move a over s to the other side of the equation as long as we know what the value of a is. In this case, a is 1. And then subtracting that from the first term easily takes us to the second term. So let's do that really quick. So essentially, it means that 1 over s times 400 divided by s squared plus 12s plus 400 minus 1 over s. So that is actually, I'm moving this to the other side of the equation. Let me simplify this first. In order to do that, we need to just take the common factor here. As you can see, the common denominator is going to be the multiplication of s times s squared plus 12s plus 400, which is the common factor, common multiplicand. Then we can divide this whole thing by the first one, which is going to be 1, multiplied by 400. So it would be 400 minus. Then if I divide this by s, I would be left by only this term that is going to be multiplied by 1. So that would appear in the numerator. So s squared plus 12s plus 400. So if I simplify this, I can get to the following equation, that s times s squared plus 12s plus 400. And I would have minus s squared minus 12s in the numerator. But then we can further simplify this with one more step. As you can see here, this s in the numerator can be simplified with s in the denominator as well. So in doing so, I'm going to simplify that really quickly. This way, we can easily see that numerator turns into a first order that can resemble some of the inverse Laplace transform equations. So let's try to solve of the full inverse Laplace transform in the next slide. So as you can see here, CS now turns into this form that we also have two equations in time domain that have, with respect to their frequency domain Laplace transform. The reason for looking at these two equations is that their frequency domain is very similar to the frequency domain compartment that we have, especially the second order roots at the denominator, which don't have real real poles are shown over there. We just need to simplify our original term and to make it similar to one of these two frequency domain terms. And in order to do that, we would need to first make the squared form in the denominator. So for doing so, s squared plus 12s plus 400, we would assume that 12 is a multiplication of 2 times s times the root, which in this case is going to be 6. In that case, I can easily write that down as s plus 6 squared, which adds 36 to my analysis, so I reduce that to keep the equality, and this also reduces down to 364. Now I can see that I can make a squared root in the denominator. So if I want to compare with what we have so far, I can see that a, in my case, is going to be 6, and w is going to be square root of 364. We're not going to actually simplify that further because that's not the main purpose. Now, we need to find out how we can actually make a term like s plus a, or a constant term in the numerator, by the way. Since this numerator that we have has a term from s, so we need to first try to make a statement that resembles this one in the numerator, which means that we need to create s plus a in the numerator, and a in this case is 6. So in the numerator that we have is minus s minus 12, and if I want to simplify that, it will be minus s plus 12, and that we need to find s plus x 6 in that, so I can actually easily convert the s plus 12 into this form, which I can extract s plus 6 from that. Therefore, I can write it down as s minus s plus 6 minus 6. So my numerator is now converted into two terms, that in one of them I can see s plus 6, and that resembles s plus a. The other one is a constant number that I can resemble that with this one. So if I simplify CS in general, after all, CS is going to be 1 over s plus numerator, in this case, is going to be minus s plus 6 divided by denominator is going to be s plus 6 squared plus 364. And the second term, it would be minus 6, similar root, similar denominator, is going to be represented here. So if I want to make use of these two equations at the top right, I need to make the similarities. The first equation that I'm dealing with over here is very similar to this one. And in doing so, I can assume that A is 6, W is 364 squared root, and K in this case is going to be minus 1. In that case, these two terms are very similar with each other. In the second, and in that case, I'm going to actually convert it back to time domain using this equation, which is going to be minus e to the minus 6t cos squared root of 364t. Moving forward, the second term has a constant at the numerator, so I can actually create kw over there, which in my case is going to be, again, a equals 6, w is going to be 364 under square root, and k this time is going to be simply, if I multiply this by 364 square root and subtract that, I can easily see that k, the w is going to be created over there. So this is the w, and k is simply this fraction. So it would be 6 divided by square root of 364. Now, I can make use of this expression then, that I have the k for that. So minus 6 divided by 364 e to the minus 6t, this time sine of square root of 364t. So this whole summation is now going to be summed up with 1 because 1 stands for 1 over s in time domain. And that's how we can get to ct in time domain. So let's move on to the second equation and question over here, which in our case, it is, again, a second order equation in the denominator. And interestingly, this time we can find real roots for this equation. So if you think closely at the roots of s squared plus 90s plus 900, if we try to find the delta for this, the delta is simply 90 squared minus 4 times 1 times 900. This turns into something positive that we can infer that it has two real poles in itself. So in our case, let's try to find those two poles. So S is going to be minus 90 plus minus square root of that delta divided by 2 times 1. So if you simplify this, you would get to minus 90 plus minus 67 divided by 2, which takes you to either minus 11 and a half or minus 78 and a half. So essentially, our denominator now is going to be s plus 11 and a half and s plus 78 point half in our case. So this is our denominator indeed. So let's try to actually recreate our original GS. GS is essentially this 900 divided by these two terms. So since we're dealing with two first order roots in the denominator, we can easily find out that this can be broken down into two parts of s plus 11 and a half as one of the roots and b over s plus 78 and a half using the partial fraction expansion. Since this is the first order, the numerator is going to be a constant. And we just need to find out what are the a and b coefficients over there. After doing so, we can easily find out that these terms individually are going to turn into exponential terms in time domain, which means that the first term is going to turn into a to the e to the power of 11 and a half t. The second term is going to turn into e to the minus 78 and a half t, and they're going to be summed up. So that is actually how they will be converted into the frequency domain, the time domain. However, in order to find out what are the A and B values, I'm just giving you the idea how to do that. Again, what we were looking for finding S in the previous expression, A over S, we just need to find a root in each one of these single order denominators. And in this case, this is going to be minus 11 and a half. And as soon as that's resolved, we just need to multiply both sides of CS, which in our case, we need to first find CS. CS is going to be 1 over S times 900 divided by S plus 11 and a half times S plus 78 and a half. So that's how we would be. So we can call it C over S plus A over S plus 11 and a half plus B over S plus 78 and a half indeed. So in order to find each one of A and B and C in this case, we just need to multiply either side by the root, the denominators. For instance, for C, we need to multiply both sides by S and then evaluate that at s equals 0. In doing so, SCS is going to be 900 divided by s plus 11 and a half times s plus 78.5. So that is actually what we have on the left side of the equation. On the right side, we have c plus s8 divided by s plus 11.5 plus sb divided by s plus 78.5. Now, if we evaluate both sides at s equals 0, we can easily see that these two terms would go to 0. And then on the right side, we'll be left at c, and the left side just needs to be evaluated at s equals 0. So if this is going to be evaluated as s equals 0, this term will go to 0, and the right side is going to be left with z. The left side is only 900 divided by 11.5 times 78.5. 900 divided by 11.5 times 78.5. So I'm not simplifying that further, but I'm giving you the idea how to find c in this case, for instance. The same approach is going to be applied to find a and b in this examples. So once all of those values are found, we can then convert them into time, and in the time equivalent of that is going to be nothing but c plus these two terms that I mentioned earlier. The time domain equivalent of this c over s is c. These exponential terms are also going to be as shown here. So let's move on to the third example, and here is another interesting one. Again, we're dealing with second order root in the denominator. So let's try to find CS in this case. We're still getting the step response of this. So C over S, or the output, is 1 over S times 225 divided by S squared plus 30S plus 225. So over here, if I want to simplify this, we need to consider this part to be shown itself as a coefficient like a over s, and the second part is going to show itself with as a first order equation divided by this second order equation. So I'm going to write it down as a over s plus the second one could be bs plus c divided by s squared plus 30s plus 225. So if I want to actually find out what are these values of coefficient a, b, and c, the easiest one is to find a over s, because that's, as we studied before, we just need to multiply s times cs and evaluate that at s equals 0 to find a. So it would be 225 divided by s squared plus 30s plus 225, which is going to be, these two terms will go away, and we'll be left with this fraction, which is 1. So a equals 1. The right side would have been multiplied by s, which in the case of valuation at s equals 0 would go away as well. So a is equal to 1. Now, if I move this a over s to the other side of the equation, I can subtract that from the main equation fraction, and then I can come up with the remaining term. So it means that bs plus c divided by s squared plus 30s plus 225 is going to be 225 divided by s times this root minus 1 over s. And if I simplify that a little bit, I have the common denominator that if I divide that by the first one, I get 1, multiply by 225, I get this, minus this divided by s, I'm left with only this term, so minus s squared minus 30s indeed. So I forgot to put s actually here. 30s minus 225. And these two constants are going to cancel each out, and I would be left with minus s squared plus 30s divided by s times s squared plus 30s plus 225. And you can see that again, we have an extra s in the numerator that it can cancel it with the denominator. So I'm going to just resolve that really quick like this. So essentially, my numerator is going to turn into s plus 30. So my denominator, on the other hand, is having a double real pole that I can simply write it down as a squared form, because if you think about this 30 is 2 times 15, which 15 squared is also showing up to here, which means that I can easily write it down as s plus 15 squared. So this cs is going to the first part of bs plus c is going to be very similar to minus s plus minus s minus 30. In this case, we can have b equal to minus 1 and c equals minus 30 indeed. So these are the coefficients that actually we are looking for in this expression. And now, furthermore, we can simplify that because we can make s plus 15 in the numerator as well. We just want to get rid of numerator as much as possible, so I can or simply write it down as minus s plus 15 minus 15. The denominator is going to be s plus 15 squared, and as you can see here, this can cancel one of these roots in the denominator. So I will be left with 1 minus 1 over s plus 15. The right side is, however, going to stay with complete squared form. Now's the time to make use of the inverse Laplace transform table, because these are the simplest form that we could get them. The first term is obviously as an exponential form that is evaluated with the coefficient of 15 over here. So we know that the expression in time, that is k e to the minus at, is equivalent with k divided by s plus a in frequency domain. However, for the second term, we'll make use of another term that has s plus a squared in the denominator. So this is double real pole, which is a special case of real pole. It's not a single pole, but double real pole. So that turns into kt e to the minus at, which shows itself in critically damped equations indeed. So if I compare this equation with the first one, I can easily see that a equals 15 and k equals minus 1. So I can replace them there to get ct k equals minus 1, so minus e to the minus 15t. So that is the first term. The second term, though, I can compare the denominator, a equals 15, and k equals minus 15. So I would again have minus 15t e to the power of minus 15 again t. So that is actually the term for the conversion of these two into the time domain. However, these were not the only terms in the CS, by the way. If you remember, the CS was this plus a over s. So if we consider a over s contribution in the time domain, it would be a, which we found a to be 1. So I would add 1 here as well. That represents that the forced response from the unit input. And the second term, which was here, was equivalent to this. And we have actually converted it back to time using these next two terms. So right now we could find the time domain equivalent of this frequency domain Laplace transform. transfer function. So using all the methods that we have learned in this tutorial in terms of converting the transfer functions from frequency domain back to time domain using inverse Laplace transform, here's an example that I'm leaving it to you guys. And you can have the detailed instructions as here. Just read it over and try to solve this equation, very similar to the ones that we did before, with a little bit more detailed analysis on the step response of a first order system. Thank you for watching. Hit like and subscribe to the channel if you enjoyed this video.